Hi everybody, welcome to this week's recitation activity. I'm going to be talking about the center of mass of a continuous object and the worksheet or problem that goes along with it. It's calculating the center of mass. So before we actually start the problem, let's just clear up a couple things. So it's asking about the center of mass of a continuous object. So first we want to ask ourselves what a continuous object means in this context. Why is it continuous? Well, what this continuous object is it falls under the classification of a rigid body. And what is a rigid body? Okay, well, a rigid body, kind of think of what the name itself means. The body itself is rigid. So, hence rigid body. So what that means is that we're assuming that this solid object, 3D object, will not move in any way. It won't stretch, it won't compress, it won't bend. There's no shear or strain. So under that assumption, if we're looking at mass density, we want to look at what the mass is at any point within the object. Then we can imagine some solid object. Some solid object, say some cube or rectangle, right? It has three faces, and what we can think of is if we zoomed in with a microscope at some point, what we'd see is every atom or particle the same distance away, and that no matter how much force I apply to any side of the object, the distance between the interatomic distances between each particle stays the same. And since it's a continuous object, we're actually assuming that this object is not made of individual discrete points, but rather mass exists at every point in space, which we know, or maybe you don't know now, but as you'll find out, is not really true on the quantum level. But it's a very good approximation when dealing with classical problems. So that's what it means by a continuous object. It really is talking about a rigid body, which can be said to have a continuous mass density. We know density, or mass density, rho, is generally written as the total mass over the total volume. But what we get in our assumption of a continuous object or a rigid body, it means that at any point, if the object has a uniform density, it means that at any point in any selected small volume you pick, you'll find the same amount of mass within that object. So if I pick some tiny little square within my object and count up all the mass, or weigh all that mass in that tiny little square of volume infinitesimal dV, I will get the same amount of infinitesimal mass dm. This can be expressed that if you have a uniform density, that another way to write this mathematically is that your mass density itself, rho, with respect to your spatial coordinates, is equal to 0, right? And why I say that? Because your uniform density is mass per volume. So it means, what I would see is if I measured the infinitesimal mass within some infinitesimal volume element within the object, that ratio will always be the same, and that ratio is mass density, which is constant. So that means if I pointed at any point within the larger volume, that number will always be the same. And so that means that the derivative of it with respect to that coordinate would be equal to 0. But anyway, none of this is needed for this problem. and maybe I'm overcomplicating it, but it's good to start thinking about things like in this sort of mathematical way, because it'll help later, especially if you're deriving things in physics 2 or harder topics. So anyway, we're trying to find the center of mass of a continuous object, which is a rigid body, right? And with that assumption, we know that our mass density itself can be written as a derivative with respect to volume. So instead of m over v, it's dm dv. And an alternative way we can write that is rho dv equals dm, right? And the units here make sense, right? Because rho is kilograms per meters cubed, and dv is meter cubed. And so you retrieve units of kilograms. And we'll need this later. The second part of this problem is center of mass. Center of mass is kind of a weird thing. I think everyone intuitively would be able to understand what it means and what it is, but then they look at the mathematical expression for it and it's a little bit more confusing. And it's understandable, and it takes some time to get used to. And in this case, we're looking for the center of mass here of this object, which is aligned with the x-axis like so, and the y-axis like so. And so that this height, which changes with respect to x, aligns, so this height, which is a function of x, the way it's lined up with the coordinate axis is then equal to y of x, which is given. And we also need that. So center mass is really useful. Sorry, I kind of went ahead, but center mass is really useful because in mechanics, any object's motion, say a baton, and it's spinning, well, it's actually spinning around its center of mass coordinate. And so if we have some coordinate axes set up like so, and we wanted to know how this object moves and track its position, well, it turns out if you know the position vector, which traces where the center of mass is at any time, and then know how much it's rotating, its angular velocity, around that center of mass, then that will completely determine the object's trajectory. You would capture all the object's motion for rigid bodies moving in space. So, meaning your object's motion is made up of less coordinates than would be otherwise necessary if your object's motion wasn't captured by just the center of motion's object, center of motion's motion through space, center of mass's motion through space, and the angular velocity of the object rotating around. So instead of needing a bunch of coordinates which track each individual part of the object from as it moves through space, all you need is one coordinate which tracks the center of mass, and then typically 3 angles which track the object's orientation through space. And those are called Euler angles, and it's nothing you have to worry about. But, and this is something I talk about in classical mechanics, but something a higher level class, but the importance of center of mass comes down partially because when we have the formulation of center of mass, an object's motion through space becomes much more simplified in the number of coordinates that you need to actually track the object's motion. So that caveat or / explanation of the importance of center of mass aside, you can actually go ahead and try this problem. And again, center of mass itself is a coordinate, and so if we have a 3D object, the center of mass with respect to your 0 point of your coordinate axes should be, say x center mass, should be some x coordinate in your x hat plus some y in your y hat. And if you're at a third dimension, it'd be some z and your z hat direction. And let's just go as r. Since, remember, center of mass is a point, and points, at least 3D points, will be represented by a 3D position vector, which has quantities associated with it. Well, this object's not moving, so its x center of mass, which we want to solve for, isn't changing with time. And so we can just apply the definition of the center of mass in order to find where the center of mass lies along the x-axis. Somewhere here, right? And so you see that in terms of what this is a weighted average with respect to mass, or sorry, position. Where the more mass there is at a position, the more it contributes to where you could think that the most likely point you'll find the mass, which is the center of mass. If you haven't taken statistics, then you can ignore what I just said. If you have, then that might make more sense. So then, when it comes to practically evaluating these things, you need to do some integrals with respect to dm. Well, the way our object is lined up with the x and y axis, we know that there's a center of mass somewhere along the x point, maybe somewhere around the center, and then some center of mass in the y. That'd be your y center of mass, your x center of mass, and then what's not really shown here is like your z coordinate, and then there'd be your third point, and that'd make your 3D point center of mass somewhere in the center. But we're just looking for where the center of mass lies in the x dimension, and so using the general definition of center of mass with an r, we're just looking at the x, so we put an x. So then, in order to evaluate these, we need dm. Well, we already talked through what an expression is for dm here for a 3D object, rho dm. And we're given rho in this problem. So then all we need is, I said rho dm, I meant rho dv. All we need is dv. Well, how do we get dv? Well, can we write v as a function of x, or a function of anything? That's the question. And then we can take the differential of the volume via the definition of a differential, and then that would be our dv, which we need because we need dv to write dm. So what's v of x? That's the question. Well, this object, if we just for a second imagine that it's a rectangle, a tall rectangle, then the volume of that is just length times width times height, right? So length times width times height. But in this case, what we have is instead some curve. It doesn't look at all like that. Sorry, that wasn't very accurate. But we have some curve like this. And this goes on both sides. And so then what we need to do is, well, we're actually given that height is a function of x. And so to get this total volume here, it's really the same as the area under the curve times the width, right? Because this curve makes some area with respect to x and y. And we know how to get the area under the curve if we're given a function that makes the curve. And then once we have that area, you can imagine that we multiply that area W times to get the total volume of that curve. And so that curve itself is described by y of x, which, due to the way we position our object with respect to x and y of x then takes the place of our height of our rectangle, h of x. And so then we know the area that this curve makes is the integral of h of x, or I should say y of x, from 0 to L dx would be the area. And then so our volume is just the width times that, width times 0 to L y of x dx. And now we actually have volume as a function of x. Even though there's an integral, it's still just a formula, right? 'Cause a definite integral is just a number. So what we have here is we know what our volume is, since we're given an explicit definition of the curve here with respect to x. And so then we can take the differential of our volume, which, if you don't remember what a differential is, a differential, say, of some general function f, which is which has its argument x and y, which are independent variables. And a differential is df, which is equal to the partial derivatives with respect to each independent variable times infinitesimal version, and then adding them. So in this case, there's two independent variables. So then there's two terms in your differential. In this case, our volume is just a function of x, and so there's only one partial derivative to get our differential dv. So using the definition of a differential, we will take the partial derivative with respect to x of w integral from 0 to L y of x dx, and then times dx. Okay, now we can move that partial derivative in, and w is just a number, so that will just disappear. Then we have d dx of an integral with respect to x dx, and so you get a cancellation of the integration, and you just end up with w y of x dx is dv. Now that we have dv, we go back to what dm is with respect to dv. That means dm equal to rho w y of x dx. And now we have that. Once we have dm, what our infinitesimal mass is with respect to dx, the coordinate, we can now actually evaluate our integral to find the center of mass with respect to x coordinate here. And so xcm is equal to integral of x dm. Well, I just wrote what dm is. It's rho w y of x dx. And so now our integration is with respect to dx, no longer dm, which is something we can actually do now. And we can also plug that in down here. I will go ahead and take the w out of the integral, and it'll be in the omega, and be the same thing, so without the x in the denominator. And so this term at the bottom is our total mass, capital M. And so all we need to do now is evaluate this integral to get what this position is. Now the integral is switched to dx. And so the only place that y actually exists, y of x exists, is from 0 to L. So we want to make our bounds reflect that. And the same goes for our denominator, 0 to L. So we can separately evaluate total mass. So rho W, and y of x is x minus 0.2 squared plus 0.3 meters. And so if we expand that, it's x squared minus 0.4 x plus 0.34. And so this is our y of x, which we want to use. To evaluate our integral. And so we use power, the inverse power rule, and we get rho W x cubed over 3 minus 0.4 over 2 x squared plus 0.34 x from 0 to L. And so we just get rho W L squared over 3 minus 0.4 2 L plus 0.34. And this is all just numbers. We can plug everything and make sure it makes sense. We could also do unit analysis and make sure the units make sense. This is a mass. Do we get mass? Well, width is meters, length is meters. And so, and then we have meters squared here. And so then we can calculate this, and you'll get a number. And we need to do the same, almost the same integral, except for there's an x involved for the numerator. And so get integral 0 of x times y of x, which is x squared minus 0.4 x plus 0.34. So we'll just distribute the x, and then you get x cubed minus 0.4 x squared plus 0.34 x dx from 0 to L. This is the numerator of our center of mass, and then we'll evaluate this, and you will get L over 4 minus 0.4 over 3 L3 plus 0.34 L squared over 2. And so then what we need to do is take this and divide it by our total mass, and that will equate to what our center mass is. And that's the whole worksheet. Now you notice this will give you a sum number along the x-axis for our coordinate axes. But remember that your center of mass is a point for a 3D object. It's a 3D point, and so you really have two other points that you didn't solve for. But we won't go into that, and that's not something you will be required to do, I think, on a test. So this is what we solved for, right? And so we know the point that the center of mass lies along for the x-axis. Alright, I hope that helped. I know it's a bit much, but I think just delving a little bit into the deeper side of it will help, can help you understand maybe the motivation behind some of these concepts. Alright, thank you.